A series is, informally speaking, the sum of the terms of a sequence. Finite sequences and series have defined first and last terms, whereas infinite sequences and series continue indefinitely. In mathematics, given an infinite sequence of numbers, a series is informally the result of adding all those terms together. A1 plus A2 plus A3 plus. These can be written more compactly using the summation symbol. An example is the famous series from Zeno's dichotomy and its mathematical representation. The terms of the series are often produced according to a rule, such as by a formula, or by an algorithm. As there are an infinite number of terms, this notion is often called an infinite series. Unlike finite summations, infinite series need tools from mathematical analysis, and specifically the notion of limits, to be fully understood and manipulated. In addition to their ubiquity in mathematics, infinite series are also widely used in other quantitative disciplines such as physics, computer science, and finance. Basic properties. Definition for any sequence of rational numbers, real numbers, complex numbers, functions thereof, etc. The associated series is defined as the ordered formal sum. The sequence of partial sums associated to a series is defined for each as the sum of the sequence from to. By definition, the series converges to a limit if and only if the associated sequence of partial sums converges to. This definition is usually written as more generally, if is a function from an index set type to a set G, then the series associated to is the formal sum of the elements over the index elements denoted by the when the index set is the natural numbers. The function is a sequence denoted by a series indexed on the natural numbers is an ordered formal sum, and so we rewrite it in order to emphasize the ordering induced by the natural numbers. Thus, we obtain the common notation for a series indexed by the natural numbers when the set is a semigroup. The sequence of partial sums associated to a sequence is defined for each as the sum of the terms when the semigroup is also a topological space. Then the series converges to an element if and only if the associated sequence of partial sums converges to. This definition is usually written as convergent series. A series and is said to converge, or to be convergent, when the sequence Sn of partial sums has a finite limit. If the limit of Sn is infinite or does not exist, the series is said to diverge. When the limit of partial sums exists, it is called the sum of the series. An easy way that an infinite series can converge is if all the n are zero for n sufficiently large. Such a series can be identified with a finite sum, so it is only infinite in a trivial sense. Working out the properties of the series that converge even if infinitely many terms are non-zero is the essence of the study of series. Consider the example. It is possible to visualize its convergence on the real number line. We can imagine a line of length 2, with successive segments marked off of lengths 1, 1/2, 1/4, etc. There is always room to mark the next segment, because the amount of line remaining is always the same as the last segment marked. When we have marked off 1/2, we still have a piece of length 1/2 unmarked, so we can certainly mark the next 1/4. This argument does not prove that the sum is equal to 2, but it does prove that it is at most 2. In other words, the series has an upper bound. Given that the series converges, proving that it is equal to 2 requires only elementary algebra. If the series is denoted S, it can be seen that therefore, mathematicians extend the idiom discussed earlier to other, equivalent notions of series. For instance, when we talk about a recurring decimal, as in we are talking, in fact, just about the series, but since these series always converge to real numbers. To talk about the series in this way is the same as to talk about the numbers for which they stand. In particular, it should offend no sensibilities if we make no distinction between 0.111 and 1/9. Less clear is the argument that 9 times 0.111 equals 0.999 equals 1. But it is not untenable when we consider that we can formalize the proof knowing only that limit laws preserve the arithmetic operations. See 0.999. For more examples, a geometric series is one where each successive term is produced by multiplying the previous term by a constant number. Example: in general, the geometric series converges if and only if an arithmetico-geometric sequence is a generalization of the geometric series, which has coefficients of the common ratio equal to the terms in an arithmetic series. Example: the harmonic series is the series. The harmonic series is divergent. An alternating series is a series where terms alternate signs. Example: the p-series converges if r greater than 1 and diverges for r1, which can be shown with the integral criterion described below in convergence tests. As a function of r, the sum of this series is Riemann's zeta function. A telescoping series converges if the sequence Bn converges to a limit L as n goes to infinity. The value of the series is then B1 minus L. There are some elementary series whose convergence is not yet known, proven. For example, it is unknown whether the Flint-Hill series converges or not. The convergence depends on how well can be approximated with rational numbers. More specifically, the numbers which make sequence too large, starts 1, 3, 22, 333, 355, 103,993. Max A. Alexeyev proved in 2011 that the series converges if the irrationality measure of is lower than 2.5, which is much smaller than current known bound if calculus and partial summation as an operation on sequences. Partial summation takes as input a sequence and gives as output another sequence, Sn. It is thus a unary operation on sequences. Further, this function is linear, and thus is a linear operator on the vector space of sequences, denoted sigma. The inverse operator is the finite difference operator. These behave as discrete analogues of integration and differentiation, only for series instead of functions of the real variable. For example, the sequence 1, 1, 1 has series 1, 2, 3, 4 as its partial summation, which is analogous to the fact that in computer science it is known as prefix sum. Properties of series. Series are classified not only by whether they converge or diverge, but also by the properties of the terms and type of convergence of the series, the class of the term in, etc. Non-negative terms. When n is a non-negative real number for every n, the sequence Sn of partial sums is non-decreasing. It follows that a series n with non-negative terms converges if and only if the sequence Sn of partial sums is bounded. For example, the series is convergent because the inequality in a telescopic sum argument implies that the partial sums are bounded by 2. Absolute convergence. A series is said to converge absolutely if the series of absolute values converges. This is sufficient to guarantee not only that the original series converges to a limit, but also that any reordering of it converges to the same limit. Conditional convergence. A series of real or complex numbers is said to be conditionally convergent if it is convergent but not absolutely convergent. A famous example is the alternating series, which is convergent, but the series formed by taking the absolute value of each term is the divergent harmonic series. The Riemann series theorem says that any conditionally convergent series can be reordered to make a divergent series, and moreover, if the inner real in S is any real number, that one can find a reordering so that the reordered series converges with sum equal to S. Abels test is an important tool for handling semi-convergent series. If a series has the form where the partial sums Bn equals B0 plus Bn are bounded, lambda n has bounded variation, and lim lambda n Bn exists, then the series n is convergent. This applies to the pointwise convergence of many trigonometric series, as in with 0 less than x less than 2 pi. Abels' method consists in writing bn plus 1 equals bn plus 1 minus bn, and in performing a transformation similar to integration by parts that relates the given series into the absolutely convergent series convergence tests. Nth term test. If lim infinity and 0, then the series diverges. Comparison test 1. If Bn is an absolutely convergent series such that C Bn for some number C and for sufficiently large n, then n converges absolutely as well. If Bn diverges and Bn for all sufficiently large n, then n also fails to converge absolutely. Comparison test 2. If Bn is an absolutely convergent series such that n plus 1 and Bn plus 1 Bn for sufficiently large n, then n converges absolutely as well. If Bn diverges and n plus 1 and Bn plus 1 Bn for all sufficiently large n, then n also fails to converge absolutely. Ratio test. If there exists a constant c less than 1 such that n plus 1 and less than c for all sufficiently large n, then n converges absolutely. When the ratio is less than 1, but not less than a constant less than 1, convergence is possible, but this test does not establish it. Root test. If there exists a constant c less than 1 such that n1 nc for all sufficiently large n, then n converges absolutely. Integral test. If f is a positive monotone decreasing function defined on the interval 1, infinity, with f equals n for all n, then n converges if and only if the integral 1 infinity f dx is finite. Corky's condensation test. If n is non-negative and non-increasing, then the two series n and 2 are of the same nature, both convergent, or both divergent. Alternating series test. A series of the form n is called alternating. Such a series converges if the sequence n is monotone decreasing and converges to 0. The converse is in general not true. For some specific types of series there are more specialized convergence tests. For instance, for Fourier series there is the Dini test. Series of functions. A series of real or complex-valued functions converges pointwise on a set E, if the series converges for each x in E as an ordinary series of real or complex numbers. Equivalently, the partial sums converge to f as n infinity for each x E. A stronger notion of convergence of a series of functions is called uniform convergence. The series converges uniformly if it converges pointwise to the function f, and the error in approximating the limit by the nth partial sum can be made minimal independently of x by choosing a sufficiently large n. Uniform convergence is desirable for a series because many properties of the terms of the series are then retained by the limit. For example, if a series of continuous functions converges uniformly, then the limit function is also continuous. Similarly, if the fn are integrable on a closed and bounded interval I and converge uniformly, then the series is also integrable on I and can be integrated term by term. Tests for uniform convergence include the Weierstrass-M test, Abels uniform convergence test, Dini's test, and the Cauchy criterion. More sophisticated types of convergence of a series of functions can also be defined. Other modes of convergence depend on a different metric space structure on the space of functions under consideration. For instance, a series of functions converges in mean on a set E to a limit function f provided as n infinity. Power series. A power series is a series of the form the Taylor series at a point C of a function is a power series that, in many cases, converges to the function in a neighborhood of C. For example, the series is the Taylor series of at the origin and converges to it for every x. Unless it converges only at x equals c. Such a series converges on a certain open disk of convergence centered at the point C in the complex plane, and may also converge at some of the points of the boundary of the disk. The radius of this disk is known as the radius of convergence, and can in principle be determined from the asymptotics of the coefficients and the convergence is uniform on closed and bounded subsets of the interior of the disk of convergence. To wit, it is uniformly convergent on compact sets. Historically, mathematicians such as Leonhard Euler operated liberally with infinite series, even if they were not convergent. However, the formal operation with non-convergent series has been retained in rings of formal power series which are studied in abstract algebra. Formal power series are also used in combinatorics to describe and study sequences that are otherwise difficult to handle. This is the method of generating functions. Laurent series generalize power series by admitting terms into the series with negative as well as positive exponents. A Laurent series is thus any series of the form if such a series converges, then in general it does so in an annulus rather than a disk, and possibly some boundary points. The series converges uniformly on compact subsets of the interior of the annulus of convergence. Dirichlet series. A Dirichlet series is one of the form where S is a complex number. For example, if all and are equal to 1, then the Dirichlet series is the Riemann zeta function like the zeta function. Dirichlet series in general play an important role in analytic number theory. Generally, a Dirichlet series converges if the real part of S is greater than a number called the abscissa of convergence. In many cases, a Dirichlet series can be extended to an analytic function outside the domain of convergence by analytic continuation. For example, the Dirichlet series for the zeta function converges absolutely when Re(s) greater than 1. But the zeta function can be extended to a holomorphic function defined on with a simple pole at 1. This series can be directly generalized to general Dirichlet series. Trigonometric series. A series of functions in which the terms are trigonometric functions is called a trigonometric series. The most important example of a trigonometric series is the Fourier series of a function.